Swayam Prabha. Digital India. Educated India.
Continuing with our definition of reed graph, right, and the contour tree. Um, so just to recap, I mean the first 1 hour or so, I wanted to introduce to you this notion of reed graph, right, with some connections to data analysis. The second hour was more about the mathematical properties, right, but we should be dying for algorithms now. So, we talk about some algorithms, right, and final applications. But before that, so I always find that it is useful to understand a structure if you can view it from different angles, right. So, here is another representation of the same reed graph. So, from now on we will focus a lot on the special case of contour tree, right, and we will go back and forth. So, when you have a contour tree, we have already seen simplification, right. So, this simplification actually lends itself, gives us actually a very nice representation of the tree, and this is called the branch tree decomposition, right. It is actually a very natural representation if you actually look at it in hindsight. So, a new example, but you should be able to quickly read the domain and the contour tree now, right. A lot of the simple examples will use the height function, right. So, this is the height function on this cactus like object, and you see that there are 3 minima and 4 maxima, right, and you already can calculate how many saddles there should be, right, based on this count of number of minima and number of maxima. So, the tree as you see is shown like any other tree, right, that we computer scientists like to see, right. But if you are a biologist, you don't care about trees that grow down, you care about trees that grow up, right. You don't care about nodes, you care about branches and sub branches and twigs and so on, right. So, that is the representation that we will go for, right. So, the branch tree decomposition will look like this. The question is, how do you come up with this representation, right. Since you have seen simplification, this is already very natural, right. So, here is another example where you show that branch decomposition explicitly. On the left you see a contour tree, right, which has 4 minima, right, and again 4 maxima in this case, right. On the right you see something called the branch decomposition. So, what do we do to get the branch decomposition? You do your leaf pruning, right, iteratively, right, until you hit the final arc that connects a minimum to a maximum, right. In this case you will see that it connects the global maximum to the global minimum, but like I said, this need not be true always, okay. As you remove the leaves iteratively, right, every leaf is together with the arc connected to it becomes a branch, right. So, let us assume that this was one of the early leaves that was removed, right. So, AE was the leaf was removed together with the AE edge, right, in order to give you a simple smaller tree, right, and then you iteratively removed the leaves. So, this branch AE branch connects itself to a parent which is given by BF, right, which itself is connected to a parent which happens to be DM and so on, right. So, the hierarchy is a little bit different now, right. So, the hierarchy has leaves which correspond to branches, the smallest topological features that you remove first. Their parents are the topological features that contain the smaller features and so on, until you have the root branch, right, which is the parent of or the ancestor of all the topological features. Does that make sense? Right. Okay. So this is a very nice representation, because once you store things using the branch decomposition, simplification is just a simple flag, right? You associate every branch, right, with some cost. We know that the cost here, for example, is f at L minus f at I, right. Removing the features is just removing the lower level branches in the tree, right. So this becomes much simpler. There is no pruning required and so on. So this is a very nice hierarchical representation of the tree, right, and it is used heavily in practice, right. The order in which you remove is leaves upwards. Sure, one can remove A, right. So if you remember the previous lecture, we were talking about a weight associated with each of these guys, right, and depending on that weight, I choose who to remove first, right. Yeah. Okay. So in case I remove B first, then what I would have got is AF as a branch, right. Okay. So there is nothing different here. It's just, you can think of it as an alternate data structure for storing your contour tree, right. Okay. So with that, let's talk about algorithms for computing deep graphs and contour trees, right. So far we have made very strong assumptions about smooth functions, Morse functions and so on, right. In practice, when you actually have data, things are never smooth, right. In fact, you sample your function at a finite number of places, right, and you somehow interpolate to get a continuous function. You cannot hope to get a smooth function at all, right. So often what we work with is a piecewise linear function, right. So like I said, data is often available as samples. The domain and the scalar function are given in this following way. The domain is often represented as a mesh, right. By a mesh, I mean like a triangle mesh, something like that, right, or a grid, right. The function is specified at discrete set of points. So either here at these locations or at the grid points, right, in this example, right. And what we essentially do is linear interpolation to fill in the function within each cell, right. So hence we have a piecewise linear function, right. So now what we want to do is to compute Reeb graphs for piecewise linear functions. So we will have to revisit a lot of the definitions and all the constructions that we saw for the smooth functions, but now focusing on piecewise linear functions, right. We will not be able to go through all of them. We will look at some key aspects, right. Okay. So that's the plan. How do we extend the Morse theoretic ideas to piecewise linear functions? The first is critical points, right. No gradients anymore. Even before we talk about critical points, what is neighborhood, right? Remember, when we talk about critical points, we were talking about pushing in one direction and so on, right? So what is neighborhood? Who is my neighbor, right? That already has to be defined explicitly, right? So here our assumption that we have the domain represented by a mesh, this will come to save us, right? So the neighborhood will be defined by just adjacent vertices, so which means you need to have notions of edges, right, in your domain, right. In this particular case, when will you call this central vertex a minimum? If all the neighbors have function value greater than me, then I am a minimum, right. So that's a natural way to define a minimum in this discrete case. maximum if all my neighbors are greater, right? But how will you extend this to 2D, 3D, and how will you talk about other types of critical points, right? So I don't want to define all these terms, right? I will let's look only at the pictures and focus on those terms, right? So the remaining is mainly for your notes for later, right? Remember, we are going to represent the domain using a mesh, right? This mesh will have some elements, right? Some cells, right? So imagine building a space. You have to build, in order to build it, you need bricks, you need some building blocks, right? Those building blocks are edges, triangles, tetrahedra, and higher dimensional analogs of them, right? These higher dimensional analogs are called K simplices. Okay? So K simplex is a vertex in 0 dimension, edge in 1 dimension, triangle in 2D, tetrahedron in 3D, and so on. Okay? Fine. So without definition, that's sufficient for me. Now with that, let me talk about what is a neighborhood. If I take a point in 2D, I focus only on vertices, right? Take a vertex in 2D. My neighborhood, right? I have two ways to talk about neighborhoods. One is called the star, right? The star is all edges and triangles and tetrahedra that contain me. Okay, so that's my neighborhood, right? The same holds in 3D, right? So all vertices, edges, triangles, and tetrahedra that contain the vertex. Okay. So these are called cofaces, if you want to look at the definition, right? So this is the star neighborhood of a vertex. Okay. The link neighborhood of a vertex is defined as the boundary of that star, right? Does that make sense? So in this example, the link is all the edges, right, that are on the boundary of the triangle that contains. So this is a triangle that contains the vertex, and here is an edge that is on the boundary of that triangle, but is not incident on the vertex, right? So I pick all those edges and the vertex also. So the vertex also comes like that. So I have a vertex here. This is an edge, right? This is an edge that's in the star, right? I take its boundary. Its boundary has this vertex and this vertex. I look at all the boundary those boundary elements which do not contain the vertex, right? So those guys, so these vertices will all appear. So these vertices will all appear in the link, right? So it's a very intuitive notion of boundary. There is a formal definition also, right? So in 3D, what will be the link? If I have a vertex, what will be the link? It will be the spherical shell around me, right? So those will be all the faces of tetrahedra, triangles, and vertices that are incident on me, right? So that's the link neighborhood. Does that make sense? Okay. So of course you can talk about things that are higher than me and lower than me. So you can talk about upper part of the star and lower part of the star. Same upper link and lower link. So we are going to use these to define critical points now. And it turns out that the definition is an equivalent to the smooth case. Okay. So maximum and minimum, kind of more straightforward, nothing much to do here, right? So maximum is where all my neighboring vertices have function value lower than me, right? But what does it mean in terms of the star and the link, right? So here is where my piecewise linear assumption comes to play. So if the function, so this is vertex V, right? And the function value here is f at V, and this is U, right? I use linear interpolation. So the function value along this edge right, can be written as, so if this is a point, if I use linear interpolation, what will be the value at a point x? Some lambda times f of u plus, right, that is linear interpolation. So, what does that mean? It means that if u has function value lower than v, then so does all the points x in the edge u v, right. So, if u belongs to the lower part of the star, right, if u belongs to the lower part of the star, then the edge will also belong to the lower part of the star, right. So, the linear that also means that the triangle, all the points inside the triangle, if this is w, if w and u belong to the lower part of the star, right. So, w, so what does that mean? If f at u, f at w less than f of v, right, that is when they are part of the lower part of the star, then the edges u v w, u v, right, v w, u v, all points on these edges will also have function value less than that at v, and all points in the triangle will also have function value less than the value at v, right. So, this entire star is lower star, right, it is below me, right. So, what this means is it is enough to check the function value at these guys, at these vertices, right, and because of linear interpolation everything else follows nicely, right. Okay. So, our initial intuition of checking the neighbors and ensuring that they are lower than me is valid, right. The same holds for minimum. I look at all my neighbors, check if they are all above me, and if yes, then I declare myself as the minimum. Okay, fine. But let us look at the same thing again, different viewpoint of the same idea, right. The minimum, if I look at all points neighboring to me, they are all above me, right, which means that the so the lower link, so the lower star is empty, right. There can be no other points which are below me, so that already means that I am a minimum, right. Nobody in my neighborhood is below me, that means I am a minimum. Okay. But let us look at the same thing in a different viewpoint, right. So, let us look at the link, right. What is the topology of the link, right. We are not going to leave topology anywhere, right. So, it will always come with us. So, what is the Euler characteristic or the number of connected components of this link, the lower link? The lower link is actually shown in bold here, right. So, what is the lower link? It looks like a circle, one connected component, maybe one tunnel, right. What about the minimum? The lower link, 0 connected components, it is empty. Okay. So, now saddle, lower link, 2 connected components, right, no cycle or anything, right. So, it turns out that this is the characterization we need. Okay. So, if I take the topology of the lower link, I calculate number of connected components, I calculate how many tunnels, I know exactly which critical point I am, and this is actually equivalent to the characterization we saw earlier with eigenvalues, right, with all that, right, the unstable directions and all that. Okay. So, in 3D this looks a little bit different. So, there is again this brown guy, right, it is coming up. There piecewise linear does throw some hard googlies at you, right. So, you need not have just 2 connected components, you can have multiple connected components of lower link, right. Like I was telling you initially that this behaves like a horse's saddle, right? A monkey will need one more direction for the tail to go down. So, there will be 3 directions in which the function goes below, right. This does not happen for Morse functions. Monkey saddles do not appear in Morse functions, but remember we are piecewise linear function. So, it can happen and there is a way to handle it, but let us set that aside now, right. So, all I am saying is that there are difficulties, right, but they can be handled in a uniform manner. Okay. Let us talk only about the simple cases, right. So, 3D minimum can have no components of the lower link. So, the lower link is just shown this way, right. So, this is just lower link. Okay. This is empty, right. So, 0 connected components. How about the maximum? The lower link has 1 connected component and it is a sphere. So, it has, what does it have? It has, it encloses a void, okay. That can also be computed. I am not talking about that, but that is different topologically, right. It's a sphere. How about the saddle? This is one type of saddle. The lower link has 2 connected components, no tunnel or anything, right. So, that is what is shown here, 2 connected components, no holes. How about the 2 saddle? How many connected components? 1, and how many holes or tunnels? It looks like there is 1 hole, right, around. So, remember hole, how you can look at it. So, so remember, you remember the equivalent of holes, cycles and so on, right. So, this has a hole. So, this hole looks like that, right. You cannot shrink that, right. So, that is the hole. So, it has 1 component, 1 hole. Okay. So, this is all visual. It turns out that you can actually compute these guys. There are algorithms. So, these are called Betty numbers, like I told you earlier. There is a nice algorithm to compute Betty numbers, right. So, it's almost near linear time. So, you can use that algorithm to compute the Betty numbers, okay, right. So, you can calculate all these guys and you characterize your critical points, right. So, first job done, we know where the nodes of the Reeb graph are, right. So, now the task is how do I compute the Reeb graph. So, again there is these things do show up. There are so called multi saddles which do not fall under one of these nice simple cases, right, but we can handle them, right. Okay. So, here are to summarize, here are the assumptions we have made, right, to move from the smooth case to the piecewise linear case. Okay. We assumed that there are no flat regions. Okay. Flat region means what? It means that f of x equal to f of y for neighboring points. We assume that this does not happen, right. So, remember from the examples I think shown about the degeneracy and so on, they often needed the fact that you have a flat region, right. We assume that that does not happen. Okay. We also assume that these multi saddles do not happen, the monkey saddle and all that does not happen. Okay. Now, why are these assumptions valid? We have a way to uniformly address the first point, right, using a technique called simulation of simplicity. This does a small perturbation, and with that you can ensure that in your data no 2 points have the same function value. Okay. And the second, no multi saddles can also be handled by explicitly by essentially the same algorithm or by splitting the saddles into simpler saddles, right. So, again this is a little bit advanced, so I will not talk about that. Okay. But all I am saying is that our assumptions are not too strong. Okay, it's okay to make these assumptions. Okay, so now about the algorithm, right? We want to construct a Reeb graph, right? First, let's talk about a contour tree because that's a building block for the algorithm to construct the Reeb graph. On the left, you see different isosurfaces of a scalar function, right? You can see that the number of components is changing, right? It is changing from 1 here to I think 4 here, 3 and so on, right? You can see that I can easily count the number of connected components. In case this is not clear, the way you count it is by looking at the number of intersections, right? This is obvious once you understand the structure of the contour tree. So, what you see here is the contour tree, right? So, this is the contour tree. Right. And we want to compute the contour tree. The first observation is that the contour tree can be written as the sum of two simpler trees, and the two trees are computed defined this following way, right? For the contour tree, you sweep and you look at how the level sets are connected with each other, right? Now, instead you look at everything below you and see how that is connected, right? As you keep increasing function value, you look at the entire domain that you have swept so far and see how that guy is connected. So, clearly you cannot have splits, right, because you are sweeping everything, you are looking at everything below you, right. So, you are only accumulating, you cannot split, right. So, you can only have merges, right. You do that in both directions, bottom to top and top to bottom, right. You get two trees, these are called the join and split trees. Okay. So, the join tree, as you can see, looks at merges in the top to bottom. So, the sweep goes from top to bottom, right, and you are looking at everything above you, right. So, when you reach, let us say, this level, right, so everything above you has merged into one component. Does that make sense? So, hence you have into two components, I am sorry. When you reach here, everything above you has merged into one component, right. So, this is the join tree. You do the same for the sweep in the other direction, you get the split tree, right. Okay. So, clearly the join tree contains all the maxima, and it contains only the one minimum, which is the global minimum, right. The same way the split tree contains all minima and the one global maximum. Everything else is missed, right. But interestingly, whatever is missed from the join tree is captured in the split tree, right. And if you put the two together, you actually get the contour tree. So, this plus this is equal to the contour tree. Okay. Now, why do I care about the join tree and the split tree, right? Because I am doing the sweep anyway, right. The reason is that maintaining connected components, right, is actually easy, right. Maintaining connected components is easy if the only operation that you are allowed are form set, maybe I should not say form set, I should say create set, right, and union, right. If these are the only operations allowed, then actually I can maintain a collection of sets, right, or a set is nothing but another representation for a connected component, right. So, if you have seen this, then great. If not, there is a nice data structure called the union find data structure, right? It's in your CLR book. You can go ahead and see it, right? So the union find data structure is a nice data structure that allows you to maintain a collection of sets, and the operations that are supported are union, create set, and find. Find is more like a query, right? So these queries are supported, right? And the union find data structure supports these queries in kind of amortized. N alpha n time, right? So for n operations, of course, for n union find operations can be done in O n alpha n, which means every operation takes only alpha n, and alpha for all practical purposes is not more than 6, right? So you can, it's like a constant. Alpha is, if you see this further, it's called the inverse Ackermann function, and it's never more than 6. So this is near linear, so you can actually maintain this very fast, right? Hence, you want to represent the contour tree as the union of a joint tree and split tree, right? So you run the unions in the downward sweep, you do the unions in the upward sweep, and then you merge the two guys to get the contour tree. Okay. So this is a very nice algorithm. I am going to give references at the last slide. This was done in 2003. This algorithm, it was already reported a little bit earlier, but 2003 was when this algorithm for computing the contour tree was reported by Carr et al. Okay. So the algorithm actually takes the same time, right? It's near linear. Well, there is a sorting needed at the beginning, so there is an n log n, but it's super fast. Okay. Okay. Can we just use this directly for Reeb graphs? So, yeah, maybe we'll go to the next slide. No, here is good. So let's think about this. What will happen if I apply the same algorithm for Reeb graphs? What is the joint tree? Remember, I track everything above me. So the joint tree will be a straight line, because everything above me is always connected. What about the split tree? Where do I have the loop? That's gone, right? So the algorithm doesn't work when you have cycles, right? It works only when you have a tree to begin with, right? So it works only for domains which are simply connected, right? So there is no hope here. So which means you have to handle the loops explicitly, right? And it took a while to recognize this, right? And here is the idea for constructing the Reeb graph, right? So the idea is to identify the loops explicitly somehow, right? And then reuse the contour tree algorithm by Carr et al. Okay. So how do you recognize the cycles to begin with, right? So let's take a snapshot, or I mean a section of the Reeb graph that's shown here, right, which shows one cycle. One of the cycles that goes from C sub j to C sub s, right? I define this loop by the lowermost critical point C sub j and the highest critical point C sub s, right? Each loop within the Reeb graph will have these guys C sub s and C sub j, and both have to be saddles. They cannot be minimum or maximum. They have to be saddles. So degree 3, right? Fine. So, locally they will look like this, C sub S will look like this, right, and C sub j will look like this, right. I can distinguish between C sub j and C sub s. How? I know my classification of critical points, right. Forget about the Reeb graph for now. I go look at every point. I can look at the lower link, upper link. From that I know whether I am C sub j or C sub s, right. I know that, okay. But even this guy will have a similar behavior. C sub x will also look locally like C sub j, right. How do I distinguish and find that I am C sub j and not C sub x? As in, I am a saddle that defines a loop and not somebody who is splitting one component into two components, right. How do I distinguish between the two? This is the key, right. And it turns out that you can actually find that by running just the union find sweep in one direction. So, let us say you run the union find sweep in the downward direction, right. This is the tree that you will get, right, because this component will merge with this guy, but the loop will essentially get squished, right, because it is and you will get C sub y will no longer be a node in the graph, but it will be in the a node in the augmented graph, okay. That is why I am showing it. C sub j will also be a node in the augmented graph, it will be degree 2, right. So, that the characterization is the following. I am looking at saddles which have this kind of a structure and is degree 2 in the join tree that I compute, right. C sub x, remember, has the same structure as here, but it is degree 3, right. So, I have a way of distinguishing between C x and C sub j, right. So, C sub j, by the way, j stands for join saddle. So, I am identifying join saddles, right, using this pass, right. So, I am reusing the contour tree algorithm to find the join saddles. Now, why are the join saddles important, right? So, if I take the join saddle and break the tree here, I mean break the graph here, I am essentially kind of performing surgery and removing one of the cycles, right. I am opening the cycle out, right, and if I remove all the cycles, I get a tree, right. So, so that is the intuition. That is why I wanted to find these C sub j's, right. So, let us say I find the C sub j's, right. Then what I do is I partition my domain such that each subdomain, right, is simply connected, okay. So, I am just showing here an illustration, right. Things are not as simple as the illustration, but you will get the idea. So, if you take this domain, how many loops should the Reeb graph have? 2 for any function, we know that, right. It need not, I mean, for the height function, of course, you see that there are 2 loops, but for any function you should have 2 loops, we know that, okay. We find the join saddles and split the domain exactly above these join saddles. So, remove, see, we have split it here and we split it here. The split can have other consequences. It can split this guy further, but that is okay, we do not care about it, right. Now, if you see every subdomain, it is all simply connected, right. No, they all look like spheres, there is no loops, right. I can individually process them, right, compute the contour tree. The question is, how do I put them together, right. So let's look at the first guy. If I've partitioned this into some small subvolumes, after the partition, this guy should get some local minima, right, at the boundary, right. So that's shown here. Just because I have partitioned it, right. So this guy should have some some minimum, right. So this is some minima. They get introduced because they are at the boundary, right. Okay. So these are the yellow ones. So I compute CT1, contour tree 1, and I compute contour tree 2, contour tree 3. Contour tree 2 has similarly some yellow maxima due to the partition, right. Does that make sense? You are creating artificially a boundary, so which means that there will be a global maximum there, right. And similarly, the CT3 will have some maxima, right. So, and you are computing all, so you have 3 trees now, CT1, CT2 and CT3, right. Well, it turns out that CT2 actually has is 2 components that can happen. CT2 is not even a tree, it is a forest. It has one component here and another component here, right. Okay. But merging this is now trivial, right. I know that every point here can be identified with a corresponding minimum from the next tree, and I just have to merge these 2 trees together, right. I merge them, I get the Reeb graph. Does that make sense? I merge them, I get the Reeb graph. So the steps here are, you find the joint saddles, right. Then you partition your Reeb graph into trees, right. This is circular, so you need to do this by locating the joint saddles. That's essentially what this means. You locate the joint saddles and partition it there. Then you compute all the contour trees for each subdomain, and then you stitch the trees together by identifying the corresponding pairs of boundary minimum and boundary maximum. You just merge the 2, right. All these operations, this operation, it takes linear time, right. This we know already is the same time as computing contour tree, right. This partition, this finding the joint saddle is just for each node you have to look at the neighbors, so it's also fast. This is the step that may take time. You have to partition it. So it turns out that this doesn't take too much time, it takes time which is dependent on the number of saddles times the number of vertices, right. So if you have too many saddles, then this is very slow, but in practice you hardly have too many saddles. The number of nodes is often greater than number of saddles. So this works quite well, okay. So this algorithm is called recon. Right, Reeb graph using contour tree. So that is the algorithm. It works very well in practice. So this was actually already an algorithm which is about 7 years old now. But the state of the art at that time took for millions of triangles, right, input with millions of triangles, the state of the art algorithms took at least about 100 seconds, as you can see here, right. Whereas this recon could do it in a few seconds, like 4 or 5 seconds, right. The black line here shows an algorithm that is fine-tuned for 2D domains, right, and hence is able to do much faster, right. Whereas recon works, the same algorithm works in all dimensions, right. It's a generic algorithm. Again, same recon applied to 3D domains. 3D domains, the algorithms go much slower, so up to 1000 seconds, right. Whereas recon again within 10 seconds, right. So the key idea is the partition and reusing the contour tree algorithm, right? The contour tree was already known. Okay. So this is again, like I said, well, six years, right? Is much faster, and to give you an idea, 4 to 6 million elements in 4 to 6 seconds, right? That's at that time. Of course, the process speeds have not increased since then, unfortunately, but number of cores has increased. So a lot of development since 2013 has been on parallel algorithms for computing the Reeb graph and the contour tree, right? So this is just a pointer for you. 2015 we had a parallel algorithm that can process up to 8 or 9 billion points in about 3 minutes on 64 cores. That is like a workstation that sits on your desktop. 64 cores. You can process really large data, and the good thing is that the algorithm does not require a lot of memory. So the RAM that you have is sufficient, right? 10 GB is what is used for this particular data set. So this is called DivCT. If you want, you can look this up. Yeah. Yeah. Right. So for that, I think the data side, that was not a large data set, but the contour tree was large. So that data, if I recall, it was only about 500. It was not even billion. It was maybe a few hundred million, maybe. That's all. Right? Yeah. It's not a big data set, according to me. Yeah. If I remember, I think it's 500 by 200 by 200 or something. So that's what, 10 to the 6. Not much. Yeah. So there are lots of applications. But I think we may not be able to cover much. It's already a little bit late. I'll talk about only one application, and we'll close there, okay? Because we already saw one different application. And when we do the hands-on session, you will actually see some of these in really hands-on, right? So let me see. I want to talk about symmetry. So one application of contour tree is to find repeating units in a scalar field. So here is a scalar field, right? That's defined over this object. I want to find the fact that M1 is a copy of M2, right? The two legs are copies of each other geometrically. In addition, the scalar field, the scalar function defined over M1 is also a copy of the scalar function defined over M2. Does that make sense? So which means that T M1, there is a transformation that takes M1 to M2, right? In addition, the transformation preserves the function values. So, right? So the function value at a point in M1 is the same as the function value at the corresponding point in M2. So we want this to be preserved. So we want to find all such regions. This is the problem of symmetry identification, right? So you can imagine that this is finding all copies. So let's say you have two lungs, right? The distribution of blood vessels in one is a copy of the distribution of blood vessels in the other, right? So I want to make sure that the geometry is a copy of the other. In addition, I want to make sure that the function value distribution is also a copy, right? I want to find such repeating units, and this can be done using the contour tree. And so the way this is done is by finding isomorphic or similar subtrees, right? You take the contour tree and you find subtrees that are equivalent to each other, right? And in graphs, we know that there are nice algorithms to find similar trees, right? Then we use that property to find this symmetry. So this symmetry actually helps because it can help us highlight these interesting repeating units in virus, right? So like virus like this, in proteins like this, which circular symmetry, corkscrew symmetry, right, translation symmetry, right, rotation symmetry. It does not matter, it is able to capture all kinds of symmetry. So, in fact, this symmetry is much more than that. This is called dodecahedral symmetry. So, you actually have, so each unit, this is a copy of this unit, it is a copy of the blue unit, it is a copy of the pink unit, and so on. And this illustration, this picture is generated by first computing the contour tree, finding the symmetric regions and highlighting the symmetric regions, right, explicitly highlighting that these guys are copies of each other. And we have done all the steps here, right. We know from the scalar field how to find the contour tree, we know how to compute the contour tree, right. We know how to find subtrees, that is kind of trivial, right, and assume that we know how to compare two subtrees, right, and if two subtrees are the same, right, we call them as symmetric copies. Now, given a subtree, how do I find a volume here? We already have that mapping also. We know for each arc what is the corresponding part in the volume, right. So, if I have a subtree, you know the corresponding subvolume, right, it is the union of all those regions from the arcs, right. So, hence you know this guy corresponds to one of the subtrees, and this corresponds to another of them, and they are all copies of each other, and we are highlighting them in this visualization, right. So, this is one interesting application of contour trees. This can be extended to time varying data also, right, to track features like cyclones over time, right. It can be used to track multiple cyclones even if they occur at the same time. It can be used to find repeating units in a molecule. So, this is a web viewer that we have developed using this idea. This can be used to find periodicity or repeating behavior in data, right. This is some flow which shows a lot of repeating behavior. So, you can find periodicity. It can be used to track cyclones, like I said, and find the tracks of cyclones also. It can be used to summarize data. So, you have data time varying, so something that some feature that changes over time, right, like over 100 time steps, right, and you know that the first 10 time steps there is really nothing happening. Then the next 20 time steps, some turbulence begins to develop, and finally the turbulence kind of fades away. We can summarize the data and into these three intervals, right, automatically, again by using the contour tree. So the several applications, I think each one will require a lot of background to explain to you the details. So instead of that, I am just going to give you some references, some reading that you can pick up if you are interested in looking at each of these applications. So the key references are here. So Harish was a PhD student at IISc. His PhD thesis was on REAP graphs. So you can find the basic algorithms for the recon algorithm and the basic definitions all from his thesis, right. So Raghavendra has a nice paper on comparing trees, right. This you can read to understand some applications of contour trees and REAP graphs. The third reference is the one that describes the loop properties, the number of cycles and so on. So if you are interested in that kind of work, then you can look at the third reference. The last two references are more generic references. This is a book on computational topology. If you are interested broadly in this topic, right, REAP graphs, there are other data structures also. There is one recent paper, this is an early version of that recent paper, on comparing distances between REAP graphs, right. This is a very nice, interesting result, so I wanted to highlight that. There are several other references. These are a good starting point for you, right. So to summarize, data is increasingly becoming large, feature rich. So, it is very important to develop techniques like topology based methods, which will give you abstract representations like the Reeb graph, right, so that you can get a handle into your data. We saw the Reeb graph in detail. We saw that it captures level set topology. We proved a few properties, very simple properties about the Reeb graph. It was very simple to define, but it turns out to be very effective in practice. Right. We have in our group developed several algorithms and implemented them also. So, if you are interested in code, that is also available. You can look at the web pages of our lab. There are lots of videos also illustrating, for example, the construction of Reeb graph, applications of Reeb graph. Some of the applications I talked about here, they are all available on our YouTube channel, right. So, you can look at that and send queries or comments definitely, right. So, I want to stop there. Any questions I am happy to answer now, quick questions about this lecture. Of course, in the afternoon we are going to look at some specific problems in detail in the first problem session, and then later we will look at kind of a hands-on session with a software called ParaView, where Raghavendra will go through some connections between topology and visualization. Right. So thank you, and